Hello and thank you for tuning in. Today I am presenting image registration work that I've done with Balbastre and Ashburner at UCL. Image registration aims to achieve spatial correspondence between voxels in multiple images. A example is a rigid registration of within subject multimodal images, for example the CT and MRIs here on the right. And another example is spatial normalization, where you build some sort of mean image from a group of subjects using a nonlinear registration approach. Image registration is an important task, crucial for many types of analysis. For example, a multi-channel segmentation routine or comparing subjects by the already mentioned spatial normalization. It has seen decades of active research with much of the seminal work taking place in the 80s and the 90s. It is still, however, a challenging task as modalities can have different distributions, for example CT and MRIs. There can be big partial volume effects, for example in very thick sliced MR images, and intensity non-uniformities, part of the MRI acquisition, can also lead to difficulties, abbreviated INUs here. So image registration is most often done by optimizing some sort of cost function. Such a cost function is shown here, where there is a fixed and a moving image, and the moving image is resampled with some transform t to match the fixed image. A cost is computed. This cost then minimized to obtain an optimal transformation. And this is a pairwise registration approach. A good cost function should have its minimum when the image is in alignment. So the sort of behavior you see here on the right. Very common examples are the mean square difference and mutual information. A cost function can also be defined in a groupwise setting. This means that the cost is taken across capital M images or channels, in the case of medical images of the same patient, say. Here, all the transformations are optimized at once. Advantages of groupwise cost functions are that they obtain a joint optimum across all images. This should, in theory, reduce the bias you might induce if you pick one image as fixed and registered images toward this fixed image. There are also more registration features in a joint optimization across all images at once. There are, however, limitations of both pairwise and groupwise methods. A limitation of the groupwise method is that its computation is challenging, as these methods often don't scale well with an increasing number of images to be registered. Many registration methods are also sensitive to large intensity non-uniformities, and an example of such a non-uniformity is shown on the right here, where there is a T1 weighted with and without this bias. They may also struggle with large offsets. We therefore propose a groupwise gradient-based cost function, and this cost function builds on the well-known total variation norm, as that you can see here in the slide. And in this paper, we perform a group proof-of-concept study on a multimodal rigid alignment, but this cost function should generalize also to nonlinear registration with more parameters. So the joint total variation is what we use to perform our multimodal registration. It's shown here, and compared to its single channel counterpart, the norm is here taken across channels, where this is the gradient of the vector valued function f. This is, as I said, an extension of total variation to multi-channel images, for example RGB, and this norm has been used in inverse problems to regularize multi-channel images, and this will then bias the optimization to find a solution where the gradient profiles align across the images. So our idea is then to use this joint total variation norm as a cost function for image registration. To justify this idea, look at the image here on the right, where I show the voxel-wise joint total variation for non-aligned and aligned multi-channel MRI images, and the bottom image has a lower joint total variation than the upper one. So to extend joint total variation to be used as a cost function in image registration, we first have to assume that we have the M discrete images, and they are actually a continuous functions over the M channels, where we get the continuous representation by interpolation, and where each function represents the same object, but that can have different fields of views or voxel size. We then define a transformation model to some mean space, mu. This transformation model is seen here on the right. It basically takes a voxel in one of the input images and transform it to the mean image. And this mean image can be built from a maximum bounding box across all the input images, or you could also pick the field of view of one of the input images. MU is the mean space orientation matrix. R is the rigid transformation that optimized for each input image, and M here is the voxel to world mapping of each input image. This gives us the joint total variation for rigid alignment, where we now have plugged in the transformation model into the total variation. However, we need to improve the robustness of this cost function, because it may otherwise struggle with the images of very differing fields of views, which is common in medical imaging, and we therefore subtract the individual total variations from the joint total variation. We call this normalized joint total variation because it's somehow analogous to what is done in normalized mutual information. We find experimentally that the normalized joint total variation does not have its minimum when we expect it to. The experiment we done to find this out is we compute the normalized joint total variation for two voxels, and we hold the gradient magnitude for one of the voxels fixed, and we then we vary the gradient magnitude for the other voxel. For example, the red line here shows the one voxel having gradient magnitude 2, which we then would assume we find a minimum at 2, but this is not the case. We therefore modulate our normalized joint total variation by the square root of the number of channels m, and as you see, the modulated version does find its correct optimum. Also, interestingly, you can look at the comparison to mean square difference here below, and you can see how there is more of an L1 behavior of the normalized joint total variation cost compared to L2 behavior for the mean square differences, which we expected, seeing total variation is an L1 type of penalty. Some implementation details, as we would like the implementation to be general and robust. The lambda parameter is estimated from the input data from each image. We use a coarse to fine scheme where we start the registration on a mean space image with quite large voxel size, and we then decrease the voxel size to the final value. We parameterize the rigid transformation using a Lie algebra, which allows us to remove a bias that could be induced in the in the mean space. And as a rigid registration is a optimization problem that does not have a lot of parameters, we simply use a Powell's method to optimize the cost function. And this is a derivative-free method that works well on small numbers of parameters. We perform two types of validations to see how our proposed cost function behaves. The first validation is done on BrainWeb simulated data. We simulate a multi-channel image that has a T1, T2, and PD weighting, 1 millimeter isotropic without noise and intensity non-uniformity. We then, for each channel, apply a degradation process. This is shown here at the image at the bottom. We start with a reference image. We then apply a random strength intensity non-uniformity, and we then simulate thick slices, which is common in hospital data, along one of the axes. We add random Rissian noise. We crop the field of view, and finally we reposition with a rigid realignment between -5 to 5 centimeters and -15 to 15 degrees. And we do this for 2,000 simulations. We then use our proposed cost function to rigidly align the images, and also cost functions implemented in the SPM12 software: mutual information, normalized mutual information, entropy cross-correlation, and normalized cross-correlation. The result of this investigation is shown here on the right. You can see that out of all the methods, the smallest absolute errors was obtained for both translation and rotation by our NJTV, normalized joint toleration method, and the red line here is an error below 1 millimeter and below 1 degree. Furthermore, to investigate the influence of the different degradation parameters, we perform a log linear fit, where we assume that the errors are independent, and we can then regress with respect to the different parameters. Here is a comparison between mutual information and normalized joint total variation, and you can see here that as the intensity non-uniformity increases, the error increases for mutual information, whilst it stay more or less unchanged for normalized joint total variation. We also see the same behavior for the amount of offset. The second experiment we perform is on real data, where we evaluate CT to MRI and PET to MRI registration. We use a patient from the RIRE registration challenge. This was a registration challenge which was performed in the late 90s, where ground truth transformations were obtained by placing fusules on a stereotactic frame used during neurosurgery. And the example, or you can see the images here on the right, CTs and the MRIs. We registered these images using our normalized joint total variation cost. We did 3 types of groupwise registrations. We did a CT and PET to MRI, so that is in total 5 images: the CT, the PET, the T1, T2, and PD weighted MRIs, where we got around 2 millimeter error. We used only the CT and MRI, where we achieved a sub-millimetric error, and we did PET to MRI, where the error was around 2 millimeters. And this compares well to the RIRE methods. The CT error is slightly smaller, and the PET as well, than the methods evaluated in this the paper. For example, mutual information was part of these methods. And a groupwise registration, including all 5 images, took about 8 minutes on a modern workstation running on the CPU. So to finish up, we introduced a novel registration cost function. It is principled, builds on a gradient-based norm, which is groupwise by nature. We showed that it was robust to intensity non-uniformities and large offsets, and also that it achieves a low multimodal registration error. A limitation of the method is that we are using Powell's method to find the optimum. The method only works for a small number of parameters, and therefore will not scale to nonlinear registration, where the parameter space is much, much larger. Future work will therefore investigate the derivative-based optimization, which would allow for performing nonlinear registration using the proposed cost function, and should also improve the convergence. The implementation of this registration algorithm is available at the following URL. And that's it for me. Thank you.